Hello, welcome to the second chapter of economic statistics. So, we are going to study conditional probability in this chapter. It's a kind of continuation from chapter 1. So, I believe all of you have finished chapter 1, but in case if you didn't, please finish it first, okay? In the first chapter, we learned basic operations, union, intersection, complement, and some basic notions like joint distribution, marginal distribution, and like outcomes, events, probability, sample space, sample size, right? So it was just laying out a fundamental foundation of probability, or in general, how to describe randomness, how we study randomness in the following chapters, right? But in this chapter, in the second chapter, we are more applied. Like, so in the previous chapter, it was simple how to calculate probability, but now we will think about more specific case where you have multiple variables and you'd like to make a decision. You'd like to compare which is better, or if two groups are similar or different, which is better, things like this. So, and then in that case, simple probability, though the probability what we learned in chapter 1 does not apply, cannot handle these applications. So we are going to extend the definition of probability to conditional probabilities. Okay, let me see. So the keyword is conditional probability. So if you're using a textbook, just search for conditional probability. Let me start with a made-up example. It's about promotion and discrimination. So suppose that we would like to study if female police officers are discriminated in their promotion decision. So by the way, it's purely educational purpose. I'm not saying they exist or they are not. Like, so it is just made up numbers. So suppose that you have data, the frequency distribution table for promotion candidates and their results are given in this table, 2x2 table, right? So 288 male police officers are promoted in the data, and 672 male police officers are not. Like 36 female police officers were promoted, 204 were not. So these are just like a number of results, their gender and their promotion results among the promotion candidates. And of course, these numbers are purely made up, right? So it's not like gender studies or political science things, not sociology. It's purely statistics, okay? Okay, now I'm going to define the events like M for male, F for female, P for promoted, okay? Then obviously, what is not defined is P complement, which means not promoted, okay? So simple, just male, female, promoted, not promoted. If you have finished chapter 1, I believe this will be a really easy question. What is the probability of F cap P? So should be simple. Use a calculator. Pause the video now and just try it, and resume the video when you are done. So okay, I'll show you the answer. I'll turn the page. The answer is, so first, like, you have to tell what is the intersection. F cap P is these 36 observations, right? We have 36 observations in this event. Okay, it's only one outcome in this event. And then what you need is the total number. 36 out of what? Out of the sum. That is simple, easy to calculate. 1200. There are 1200 observations in our data, but out of them, 36 were female promoted candidates, right? So that is 3%. Okay, now you remind what you learned in chapter 1. So then, pretty much the same question. What is the probability of M cap P, M intersection P? M stands for male, P for promoted. Again, pause the video if you need time. Let me show you the answer. So this is this outcome, this event, M intersection P includes only one outcome, 288, these observations, out of the same 1200, right? So out of 1200, 288 are male promoted candidates, okay? Which is 24%. Okay, so calculation is easy. Algebra is super easy. Now let's interpret this. What we just calculate is the probability of promoted female officer is 3% and promoted male officers is 24%. So it's 8 times more than that of female. What do you think? Do you think it is an evidence of discrimination? Everything else being the same, so it's like vacuum state. There is nothing else. So all male female are identical except for their gender and their promotion results. So is this probability an evidence for discrimination? Do you think female officers are not treated well? Statistically, okay, the answer is no. I'm not saying there is no discrimination, but these numbers are not comparable. You cannot compare these two probabilities because when you see there are 8 times more male police officers, and first you have to think about the underlying experiment. You randomly choose a candidate for promotion, and if he or she is female and promoted, you count F intersection P, and male and promoted, M and M intersection P, right? Then the difference in their probability not only comes from it comes from whether they are promoted or not, but at the same time, just there are much more male police officers than female. It's pool size matter. It matters that pool sizes are different, so we cannot compare that. Just if you randomly choose any police officer, there are more male officers, right? So it is more natural that there will be more male and promoted police officers just because there are more male, right? Even though promotion decision is purely independent, still the pool size must be adjusted, right? So it's not an evidence. I'm not saying it's fair or not, but the comparison is not statistically correct. That's what I'm saying, right? So just because there are more male officers, so as a result, there will be more male promoted officers than female. Okay? Then what can we do here? The the result, what we want here is more carefully. It's like we randomly choose a person, a candidate, and check if the candidate is female or promoted, okay? But that's not what we want. We would like to change our experiment. We would like to choose a female candidate and calculate their probability of promotion. And we would like to define another experiment that we randomly choose one male candidate and then check if he is promoted, right? So simply speaking, you know the answer. I believe you guessed better comparison than these numbers. These numbers use the same denominator, 1200, but you know the better way is like this. What you want is among 240 female candidates, 36 were promoted, which is 15%, right? So out of 240, so the denominator is different. This is the pool size. This is the pool of female candidates. Similarly, for male, now you have to change the denominator because there are more male, right? So out of 960 candidates, 288 were promoted if he was male. That is 30%. So this is better comparison, right? So it adjusts the pool size across gender. So that is the conditional probability. It is change of the experiment, right? Like not just randomly choose anyone, but you randomly choose given a condition. Randomly choose an officer given that he is male or she is female, right? So for events, so like definition is like this. A conditional probability of A given B is probability of A occurring when given that B has already occurred. You are using B as a condition. B already happened. You know that it happened. So that is condition, right? So you know this knowledge, this condition when you experiment, when you do the experiment. And we denote this as probability of A given B. Like you use like a vertical bar to denote, to separate the main event from the conditioning event. Okay? So then, back to our example, what happened? We would like to calculate, so in here, 15% is the probability of promoted officers among female candidates. Okay? So successful promotion among female. That means you randomly choose a candidate, but not anyone. You choose female candidates. So when you generate an experiment, you know that what you are choosing is the person you are choosing is female. You already know that. So that's kind of a different experiment. Similarly, 30% is coming from a different experiment. Now you are randomly choosing a candidate who is already known as male, right? You look at the gender first and then choose among male first and then check promotion results. Promotion result is unknown when you randomly choose. So understanding the experiment, what is the experiment, is important here. So they are just different experiments from unconditional probability. Okay, right? I think it suggests what we'd like to do, and the definition is pretty natural, but it becomes complicated when we start to use the notation and more difficult terms. But the idea is pretty simple. Okay, then how to calculate the conditional probability? Idea is also pretty simple. The idea is when you choose a random person, like when you choose a random female officer, female candidate, you don't care about male. You are not looking at the male officers at all. So delete the observations that do not satisfy the condition. That's intuitive. You restrict your focus on female. So male, you are restricting, so the condition is male. Given that a candidate is male, you are looking at promotion, so female observations can be deleted because you don't look at that. Just delete that and recalculate probability only using the observations that already satisfy your condition. That's all. So the denominator should be different because you deleted this much observations. So the denominator is different, and of course numerator is actually the same, right? So compare. Here, numerator is 288, but denominator was everyone, including male and female. But now, given the conditional probability, you get the same numerator, but denominator is different. That means what we are doing is basically restricting the pool, not our event. The probability we would like to calculate actually is the same, right? But we would like to adjust our restrict our focus. So then you try this. What is the conditional probability of promotion given that the candidate is female? Okay, so simple. So also I'll give you, please pause the video to do some algebra and continue when you are done. So let me tell you. So the condition is female. That is, we only need this column, the second column. Male observations are unnecessary. You can just delete them. Okay, so delete male, and then you get this. And among female, the probability of promotion is 36 out of 240. The old female candidates. That is 15%. Okay, so also compare this with our previous calculation. 36 divided by 1200. 36 is the same. Now we have the same 36 in the numerator, but denominator is different. So that's the difference between unconditional and conditional probabilities. Okay. And what's actually more confusing, also confusing, is the role of the first event and the second event in the notation are very different. They play totally different roles. So probability of P given F is different from probability of F given P, because as you see, the second event is the condition. So this condition and these conditions are different. So you are restricting your attention to different types of people. So of course, they are about different probabilities. Okay, let's just try to calculate this probability of F given P. That means we are looking only at those promoted cases, right? Delete the second row, and then count how many female. That is 36, right? So condition is P, delete P complement, and among the remaining, those who satisfy the condition, calculate the ratio. So in this case, again, the numerator is the same, 36 as before, like this. 36 is the same, but denominator is now these two. Sum of these two, not these two. So as a result, it's different, 11.11%. Excuse me. So as you see, P given F is different from F given P. So they are different, pretty important. So general formula. So I hope you get the intuition. It's not that difficult, right? But now as a teacher, I have to formulate that as a general formula, which is here. Probability A given B should be, first, denominator must be frequency of B. How many times B actually happened. So because all the other observations will be thrown away, right? I only use the observations that satisfy condition B, and in the numerator, I include A and its interaction and B, which means this is the observations where A and B happen at the same time, right? So intersection means A and B. A happens and B also happens at the same time. So in the numerator, we use A and B at the same time. Okay, so out of the data observations where B already happened, how many times A additionally happened, right? That's numerator. This is conditional probability. So In this video, I defined the basic idea of conditional probability, which is pretty straightforward, very intuitive, and you can see it should be very useful in many applications. So, and we are going to study more interesting properties and things in the following videos. Okay, I'll stop here and I'll see you in the next one. See you, bye.